We've been working with graphing and writing equations for exponential functions. Today we're going to start solving some exponential equations. You can see that we have our variable and an exponent, which we haven't really had to deal with solving these types of things before. So we're going to start with something like this. We see 6 to the x power equals 6 to the 5th power. Well, if x is 5, then we get 6 to the 5th power equals 6 to the 5th power, and this clearly is going to be the same number because it's exactly the same thing on both sides. So x has to be equal to 5. X equals to 5, and we get the same number on both sides, and that's our solution. Let's think about what would take to get the same exponent here. We get 4 to the 10th on the right side. In order to get this exponent to be 10, we would need x to be 2, because that would be 2 times 5, which is 10. So x equals 2. And then on this side, we can see that we have a little bit more, and we're starting to get more and more complex. And so I want to kind of rewind and think of an idea that will help us set this up and be able to solve that. So let's go way, way back here. When the base was the same, the 6 and the 6 were both exactly the same, our thoughts relied entirely on the idea that this exponent needs to be the same as that exponent. So in the end, for our solution, it doesn't even matter what the base was because they were the same. We just said that our x has to be equal to 5. Now, if the bases were not the same, say this was a 5 or a 3 or something like that, we couldn't do that, but as long as the bases are the same, we can do that exact same thinking. So let's set this one up. The 4 and the 4 have the same base, so the 5x and the 10 must be equal to each other. That gives us this equation. 5x equals 10. This exponent must equal that exponent, and we can solve this by dividing by 5, and that gives us x equals 2. So now we're going to use that strategy to solve the rest of them that we have. As long as the bases are the same, then the exponents must be equal to each other. So in this case, 4x must be equal to x plus 9. This exponent must be equal to that exponent because the bases, again, are the same. All right, this gives us something to solve, so we'll subtract x from both sides. That gives us 3x equals 9, and then we'll divide by 3, and that gives us x equals 3. So by getting the bases to be the same, or thinking about that, it's made our work much, much simpler. Let's take a look at a couple of examples now that the bases are not the same. And we're going to have to change the equations so that they are the same in order to be able to use the thought that we just had. You'll notice that we have a 7 and a 49 as our base here, and that doesn't work for us to set up this exponent and this exponent equal to each other. So we're going to change this so that it has the same base as that. 49 can be a 7 to some power. So I'm going to write it this way. 49 is 7 squared. That gives me a base of 7 here, and I have a base of 7 over there. So we have 7 to the x minus 5 equals, all right, now we have to be very careful when we do this that we don't lose parts of this. 49 is 7 squared, but that's not all I have right here. So I like to put this in parentheses and really highlight what I'm doing so I get the same base, but then everything outside there, I'll put it outside the parentheses. Now, we need to know the power rule. So really quickly, if you need to know more about this, then go watch a video about the power rule in exponents. But when we have an exponent raised to another exponent, then we can multiply those two together to simplify this expression. So we have 2 times x, that would give us 7 to the 2x. And over here we have 7 to the x minus 5, and now we've set it up so it has the same base. That allows us to use our line of thinking where this exponent must be equal to that exponent. That gives us x minus 5 equals 2x. We'll solve this by subtracting x, and we see that x over here must equal negative 5. You can switch that around, x equals negative 5 if you wish, and we're done with that one. Let's move on to the last one. You'll see we have, again, not the same base. This is a 27 and this is a 9. Now 27 is not 9 to some power, at least not easily. So this one is a little different. I'm going to break down both of these into a smaller base so that they have the same base. Now 9 can be broken down into 3 to the second power, 3 squared. 27 also can have a base of 3. That would be 3 to the third power. So we've gotten these two things now that have the same base. We need to make sure again that we don't miss any of the other pieces and we don't lose them. So this x is still out there, and this x minus 2 is also still out there. Okay, let's use the power rule again. These exponents multiply. 3 times x would give us 3x, so we have 3 to the 3x power. This 2 and the x minus 2 will multiply. Let's do the distributive property real quick over here. 2 times x minus 2 gives us 2x minus 4. So that would be 3 to the power 2x minus 4. We now have the same base again, so we can set the exponents equal to each other. This exponent must equal that exponent, so 3x must equal 2x minus 4. We solve that by subtracting 2x, and we get x equals negative 4. Now, these can get pretty complex. There could be lots of different pieces, so I just like to break them down little piece by little piece and then combine them, simplify them until we have them in a form that works nicely. The next ones we're going to be working with negative exponents, and we might use a graphing calculator to show you how to solve these with graphing like we did a couple of sections ago. Thank you.